Okay, I want to start. Okay, sorry about that. That was for the homework 3, but I'm doing homework 2, so let's start looking at the solutions for this. Okay, so we want to show, U measures the concentration of substance. We want to show that the amount of substance over this interval is conserved. Okay, so let me just read the question one more time. So assume that U satisfies this diffusion equation and that U measures the concentration of some substance. If we know that that the x derivative at A and the x derivative at B are 0, we want to show that the substance, the amount of substance over that interval is converged. So just physically, when we say these derivatives are 0, that's saying the flux at those points are 0. So there's no inflow or outflow of this substance, at the boundaries. So physically, conservation-wise, so this is one of the things I like about this class, is because we have a very good, if we are able to translate like the physics statements to math and the math statements to physics, or it doesn't have to be physics, it could be biology or whatever it is. But if we can translate the math to the physics or the physics to the math, then we can use our intuition for either one of those to answer questions in either domain. So intuitively, if a substance satisfies the diffusion equation, which we saw is a combination of the diffusion equation is a combination of a conservation law plus the Fick's law of diffusion. If a quantity satisfies the diffusion equation, and we know that there's no substance passing through the boundaries A and B, that is, no substance coming in and no substance going out, well, just by physical conservation, the amount in that interval should remain the same. Okay, and what we're going to show is that the math also backs that up. So there's sort of two things going on. The math predicts what should happen with the physics, and the physics sort of predicts what should happen with the math. So I really like how it kind of how they sort of reinforce each other. And then it's interesting when that kind of breaks, when there are differences, to see what those differences are and what they mean. One of those would be how the diffusion equation has infinite propagation speed of singularities. But anyways, let's just compute this. So I'm going to follow the hint. It says to compute this right here. Okay, so what is the hint getting at? This quantity right there, that integral, is the amount of substance on that interval at time t. We want to compute the derivative and show it's equal to 0. So we will show, following the hint that the excellent instructor left, following the hint, we will show that, I'm just going to copy and paste this, that this equals 0 for all t, which shows that that this is constant, shows that the integral is constant, but that is exactly the amount of substance over that interval. The wonderful professor did not come up with a very precise way to talk about this. The amount of substance. Okay. So, indeed. I like to say indeed a lot. It just means I've said something, and it's true. Indeed, here is the computation. Indeed, it is right and just. Okay. So, so what we want to do is we want to put the derivative on the inside of the integral. I should be assuming here, I should make an assumption here that u, the derivative of u with respect to t, is continuous. I didn't say that explicitly, but that's one of the things that we've learned, that the solution to the diffusion equation is smooth for t in the x and t variables for t greater than 0. So really I need to say for t greater than 0, because remember, when t is equal to 0, this could be a complete mess, but we only care about for t greater than 0. Okay. All right. And maybe I'll explain a little bit about that in a minute. So now we want to compute the derivative. Indeed, for t greater than 0, since the partial derivative of u. So I have a command up here, PTT means the second partial derivative, and PT is just going to give me the partial t derivative. Since this is continuous, and the interval a to b is a bounded interval. So by the way, going with this sort of stream of consciousness that are these Rob Types videos, I'm saying this because these are the rules that you need to be able to interchange the order of integration and differentiation. And let me just tell you why that's true. So we're going to go to the Leibniz integral rule here, or Leibniz integral rule. This is the general form here, but notice here a of x and b of x have to be actually we want something like this. Okay. So it says when we can do this. Let's see. In this special case, when this is constant, so it should say when this is allowed. So we need this to satisfy something, but it's not. What is happening? So I think this is the form here. Okay. So let f of xt. So the variables are a little bit different here. In what we're doing, x is the variable of integration and t is the variable that we're differentiating. So the roles are backwards, but I'll let you work through that. Let f of xt be a function such that both f and its partial derivative are continuous in t and x in some region of the xt plane. Okay, and so that's what we have here. We're assuming that the t derivative, not assuming, the t derivative of u is continuous in the t and x variable. Okay, from what we've seen in class. Okay, so sorry about that. So in order to be able, so for over a finite interval, in order to be able to exchange the order of integration and differentiation, this function needs to be continuous in both variables, which it is. It's continuous. The t derivative of u is continuous in the t and the x variable. Okay, I guess we've talked about how it's smooth in the x variable and smooth in the t variable, but we haven't talked about how if you take the t derivative, it's also continuous, and it is continuous. The t derivative is continuous in the x variable, but it's true. Okay. Anyways, since the partial derivative of u is continuous, we can interchange the order of differentiation and integration. And so now this is the integral x equals a. And then on that web page, you can go down to see what happens if you're integrating over an infinite domain. Okay, so now we're going to have pt u of, I'm going to write it like this. Okay. But now, let me just, you know what? Let me write it like this. Since u satisfies the diffusion equation, this is okay, since u satisfies the diffusion equation, this is, I'm so bad at spelling, sometimes I think I'm going to write it like this or something. Anyways, I don't know what made me think about that. It's because I don't have anybody looking at me, so I'm rambling, I believe. I need to actually take this away. Okay, this is equal to this integral. And then what is it equal to? It's this right here. Now I'm going to keep this, but I'm going to go ahead and put the argument here. But that is in the wrong spot. Okay, so let me see how that looks so far. I haven't compiled recently. Okay. Okay, this is good. But now what we're going to do here is we're going to use the fundamental theorem of calculus. It's x derivative, x integral, so we can use the fundamental theorem of calculus. So by the fundamental theorem of calculus, this is... So I don't typically like to just write an expression. I like to have an equal sign when I have math like this, sort of, down on the next line and centered and indented. It's just what I like to do. So it's going to be equal to k of x, px, u of x comma t, and then there's going to be the vertical line. So you can either do like the pipe command, that, or you can do \vert, and we're going to go x equals a to x equals b, and this is equal to k of b times the x derivative of u evaluated at bt minus k of a times the x derivative of u evaluated at at, and you know what, I'm going to need new lines. And because the derivatives, the partial derivatives are 0, this is equal to, okay, this is 0, this is 0. Okay, so again, what I mean here is the assumption is that these are equal to 0. Really should say for all t to be more explicit, but it doesn't put any restrictions on t. And this is equal to 0, and that's what we wanted to prove. So just to let everybody know we're done, I like to write as desired here. Okay. There we go. Okay, that is the solution for that equation. All right.